Okay, so here we go. I want to. Okay, I want to get you through. We got some things to cover. Do people need to move? Is this a good spot? Evaluate right now. Is this a good place for you to be?
Yes.
Okay.
I don't know.
Okay. What we're going to look at today, proving triangles are congruent much more conveniently than we did before. Now, how do you notice that, in case you forget what we're doing, I've got the objective on the board up there for you. Yeah. So, and if I don't have it up there, remind me because I'm supposed to. So if it's not up there every day, tell me and I'll write it up there. All right.
Oh, this new thing, huh?
It's a new thing. Yeah.
The teachers have to do it. Objective.
Okay, so these things, they come and go. I would like to look at a couple things here. Whoops, gotta get rid of that. Okay, so proving triangles are congruent. Now, Monday we talked about this. We did a bunch of examples, and recall that when we wanted to prove that triangles were congruent, the only way we had was to show that all of the pieces of one triangle, all three sides and all three angles, were congruent to the 6 pieces of the other triangle. And then if all the parts of one triangle were congruent to all the parts of the other triangle, we were able to conclude that the triangles had to be congruent, interchangeable. Okay, that's a pain. That's not often easy to do. We don't have to do that anymore. Today I'm going to give you 4 good shortcuts that allow you to only need, instead of all 6, you only need 3 parts of one triangle congruent to 3 parts of the other triangle. Now, not all combinations of 3 parts work, but out of the 6 possible combinations, 4 of them do work. Okay, and at the very end, I'll summarize for you which are the 4 that work and which are the 2 that don't. So the first shortcut we're going to add is this side, side, side postulate. You don't have to, when you're doing the problems in Chapter 4, and I don't know how many of you have gotten a start on this, but when you're filling in the blanks on the proofs, when this is one of the reasons that you're adding to the proof, don't bother writing out, I mean you can, and I think I've got it set up so it'll be right, but you don't have to write out the whole thing. Just write SSS. Each of these triangle congruence reasons that we're going to talk about, these shortcuts, is going to be summarized by just a string of 3 letters. That's all you got to put. Okay. The side, side, side congruence postulate, or SSS, just says if 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. So, for example, these 2 triangles are congruent because look what we're told here. Look at the markings on the triangles. Because this AB, side AB, has 1 congruence mark on it, and so does side ED. Remember, that tells us those 2 are congruent to each other. The base of the top triangle is congruent to the base of the bottom triangle because they both have 2 congruence marks. And then the right side is congruent to the right side. That's all we need. We don't have to know anything about the angles. If we know that the 3 sides are all congruent, then we can guarantee the triangles are congruent. That's a good shortcut. Okay, so how could we, and we'll go through this pretty quickly. This is a relatively simple one. How could we show here, given this information, that these 2 are congruent, those sides are congruent, and the length of QS and US are both 10? How could we prove that those 2 triangles are congruent? What do you think?
2 of the sides are given.
2 of the sides are given. Good. Now, how do we get the 3rd? I mean, it's almost so obvious. You may even just be thinking it's already given to us, and it's not technically. We haven't been told that those are congruent yet. But what have we been told about those 2 other sides? Same length. And if they're the same length, what does that tell us about the sides? They're congruent, aren't they? Right? So we could add that. And so if we want to look at a proof, it might look like this. We're going to make our 2-column proof with our statements and our reasons. Well, we're given some stuff. We always write that down first, the given stuff. And then if this segment is equal in length to this one, well, if they both have a length of 10, we know that they're equal. We can skip this step, honestly. This is a non-step. I didn't make this particular slide in the PowerPoint, and I would not have even included that. Technically, we probably have to say, yeah, because they both equal 10, they're equal. But that's such an obvious proposition there that we could probably just leave that one out. Yes, ma'am?
Isn't it if two sides are congruent, then the third side has to be?
No.
Why not?
It's not. It's if two sides are congruent in given certain situations. Well, here's why. I'll draw you a picture. Good question. If two sides are congruent, is the third side congruent? Well, let's draw. Let's do this. Actually, we got. There's two sides to a triangle, right? Now I'm going to copy those two sides. So here's this one. Let's see. I'll move him over there. I'm going to copy this one. Move him over there. But I'm also going to rotate this one. Say like that.
That's cool.
Okay. So now, wouldn't you agree that those two? Oh, I think I. What did I do? Messed it up. Oops. Okay, so everybody agrees those two segments are congruent, right?
Right.
Okay. But then is the third segment that connects them going to be congruent?
No.
No, it's not. So I need a little bit more than just two sides. Does that make sense?
Yes.
Okay. So I do know then that segment QS and segment US are congruent by the definition of congruent segments. If congruent segments if segments are equal in length, then they're congruent, right? By definition. And then finally, once I add that other little piece of congruence information, if I say that, now I know the triangles are congruent by side, side, side. Okay? Make sense? All right. Oops. Okay, here's another one. So we got side, side, side. Now we get side, angle, side. And the position of the A is important here. It has to be between the S's, because what this really says, the side, angle, side postulate says, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. What do we mean by included angle?
Like the degree of it?
No, not exactly. Let me go back to the previous slide for just a second here, and let's take this last triangle we dealt with. Like right here, for example. If I'm talking about sides QR and RS in this triangle, what's the included angle? R, yeah, because R is the angle that's between those two sides. Does that make sense? Okay. Now, if we're talking about this side, let me draw these. If we're talking about this side and that side, then this is the included angle. But, for example, that would be a non-included angle, right? Because it's not between the two sides. And so would that. Make sense? The included angle is the angle that's formed by the two sides, between the two sides. Okay? So here's an example. Triangle ABC is congruent to triangle ZYX here, because look at this. We've got the BC is congruent to XY, AC is congruent to XZ, and the included angles, the angles between those two congruent sides, are both congruent also. Now, do you see that if I had said instead, if I had drawn a picture where that was the congruent angle and not that, that wouldn't have worked, would it? Because then I've got two sides in the included angle being congruent to two sides in the not included angle. So that wouldn't have worked. Okay? But that does. Does that make sense? Okay? You'll get this. It might seem a little strange at first, but once you get going on these, I don't think you'll have any trouble with it. Okay, let's try a proof. Now I want you to just stare at this for a second on your own first. See if you can, given this information up here, we're given two segments as being parallel, and they're already marked on the triangles for you. Given two pairs of congruences, can you find a way to prove that these two triangles, the left and the right, are congruent to each other? Don't say anything. Just kind of stare at that for a second and see if you can come up with a plan. Let me move this out of the way. We need three pieces, right? And the only tricks we have right now are side angle side and side side side. Okay, take 10 seconds, turn to a neighbor, and see if you're on the same track. See if you're thinking the same thing. Share your ideas. Make it quick.
Oh, yeah.
Okay. Who wants to take a stab at this? What do you think? What do you think? How could we get a third? Is there something else up there that's not given to us directly, but that we can show pretty easily? Yes, sir.
Angle 1 and 2 are congruent.
Yeah, good. Now, why are angles 1 and 2 congruent? What do you think? Vertical angles, yeah. So we can do this. If we're able to link those angles, we've got it, don't we? Now we've got side angle side congruent to side angle side. Make sense? Okay? All right. And notice that when we want to say this congruence statement here, we got to be careful with this. I want to, this is something that it's easy to overlook. I can say that triangle VXW is congruent to triangle ZXY, but I couldn't say, for example, VXW is congruent to triangle YXZ. How come? Because it's not. Yeah, it's not. You're right. Because when I line these triangles up, I've got to have the congruent parts overlapping, right? So if I pick this triangle up, in order to get it to line up with this one, I'd have to flip it around and stick it down like that. Does that make sense? So we can see that the V would have to line up with the Z, wouldn't it? And the X would line up with the X, of course, but then the W would have to line up with the Y, right? Does that make sense? So that one wouldn't work. We got to be careful how we say the congruence in the end. All right? If we look at a quick two-column proof of what you just told me, well, we're given some stuff. You said we could set angles 1 and 2 equal to each other, and the reason would be vertical angles. And then finally, the triangles are congruent by side angle side. Okay, let's try another one. Try that one. Think about it for a second, and then compare notes with your neighbors. See if you guys can come up with the same idea here. This one's maybe just a little bit trickier in a way because it's not a reason that we've probably talked about before. And where are you going to find all these reasons for the proofs? On the paper, yeah. Which is also online. If you need to either look online or print out another one when we're in the lab, that's fine. Okay, share your thoughts here. What do you think? Talk to each other. Liza, put that away. Okay, who's got an idea? This one's a little different. Yes, what do you think? Kelly?
You say which one's different?
No, who has an idea about this? How could we do this?
Don't you know the third one is the same because it's the same line right there?
Yeah, good. Okay, perfect. We can see that the third side of each of these triangles is the same side. They share a side, right? And so the way we would show this, by the way, on the picture up here, is like this. We would just write in a triple congruence mark, and being there's only one of them up there, it means that it's congruent to itself. Okay? That makes sense. It's a pretty obvious reason, but when we have to write something down in the reasons category for the proof, what's that going to be? Well, I'm going to pull up the list, and you tell me what it is. What's the reason? Oops, that's a little too big. About that. What's the reason for that? Yeah, it's the reflexive property of congruence. The reflexive property of congruence is a really obvious one, and some of the really obvious ones just get lumped together up here at the beginning under not even a chapter, just general properties. Reflexive property of congruence says for any geometric object, A, regardless of whether it's a angle, could be a segment, could be a triangle, could be a quadrilateral, doesn't matter. It's always going to be congruent to itself. It's an easy one to remember because it sounds like reflection. If you look in the mirror, you're seeing your reflection, which is obviously a perfect, if it's a perfect mirror, it's a perfect image of you, right? You're congruent to your own reflection, of course. And so that's how you might remember that. This middle one we're not going to use very much while we're here. Symmetric property of congruence just says if geometric objects A and B are congruent, then I can say A is congruent to B, or I can say B is congruent to A. I mean, duh, that's not a big deal. We don't use it much. The transitive property, we've already talked about once this year, but maybe I'll just mention it again. This is the one that whenever you talk about a transitive property in math, whether it's congruence for geometry or equality for algebra, it means we're going to transfer some property, transfer some relationship from one object to another to another. For congruence, it just says if A is congruent to B and B is congruent to C, then A is congruent to C. So it's like we're transferring the congruence from A to B and from B to C. Therefore, it's from A to C, right? Okay, so back to business here. So if we want to look at how this one would show up as a proof, we got the given stuff. Segment RT is congruent to itself by the reflexive property of congruence. And then what's the final answer? Side, side, side. Yeah. Three sides of one triangle congruent to three sides of another triangle. So the triangles are congruent. Okay, what about this one? We're told that DR is perpendicular to AG, and that segment AR is congruent to segment GR. So we got two pieces of information there. Can we turn that into enough for us to show the triangles are congruent?
Yes.
How can we do that? Mr. Bacon, what do you think? Get us started. We need three things, right? We need to get three parts of one triangle congruent to three parts of another. Right now, we've only got one. Okay, what do you think?
Right triangle.
Oh, okay, good. What else?
They share the line.
Okay, good. So we got two things. That's it. We got they share this side, DR, so that's congruent to itself. Okay, so we can do that. And then Biget's telling us that we've got a right angle here, which means that must be a right angle, right? Because if two lines are perpendicular, they form right angles. And if they're right angles, all right angles are congruent. And that's one of the things on our list. It's what do we call it? Congruence property for right angles, I think. It's on the list, though, and it just says all right angles are congruent. So we're able to say that. And now what's the shortcut that allows us to say that these two triangles, the left and the right, are congruent? SAS, side angle side. Right? Make sense? Okay, I'm just going to skip through that. We'll just do that, go on to the next one. Okay. Okay, we're going to get two more. Now we've got, so we're going to end up with these four. We've got side, 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 SSS, SAS, ASA, and AAS. Now, before we go any further with this, I'm going to give you a way to kind of remember what all those are, because we get a lot of them. Four of them is maybe a little confusing. Now, let's look at, what did I do? Okay, well, I did. I deleted the wrong thing, but that's all right. So what are the ones we have? First, we had side, side, side. Then we had SAS. And then now we're getting two new ones. We're getting angle, side, angle, and angle, angle, side. Okay, now there are 6 possible ways that you could build relationships between 3 parts of one triangle and the other. Okay, the other 2 are angle, angle, angle. And then the other one, I'm going to write it in a specific order. We could either write it as ASS, or I'm going to go ahead and write it this way. How about instead? And if you want to remember the two that don't work, well, one of them is pretty obvious because the one that spells a naughty word is the one that doesn't work.
Which one?
If I write that the other direction, pick it.
Yeah,
Get with the program. So that's one you can easily remember. That one. Hey, Shandy, can I get you guys to focus up here, please? Thanks. So here's one that doesn't work. That's an easy one to remember. And then angle, angle, angle is actually pretty easy to remember also. And here's how you can remember that one. If I draw 2 triangles, like let's draw a small triangle and a scaled up version of that triangle. So pretend those are scale versions of each other. Are the angles different? If I grow the small triangle to the big one, do the angles change?
No.
No, the angles all stay the same, don't they? So clearly, angle, angle, angle doesn't work, because when all 3 angles of one triangle are congruent to 3 angles of another triangle, we can easily see an example there where the triangles are not congruent. Those definitely don't overlap, right? So these are the 2 that don't work. It's almost easier to remember the 2 that don't work, and then any other possibility does work. Okay? All right, so using these 2. Well, the first one is angle, side, angle. Now you got to be careful with this one too, because it says if 2 angles and the included side of one triangle are congruent to 2 angles and the included side of the second triangle, then they're congruent. Now, what do we obviously mean by the included side? The one in between. Yeah. So for this top triangle up here, we can see that if the 2 congruent angles are A and C, then we're talking about the included side being side AC. The other 2 would be non-included sides. Okay? So here's an example where it would apply. Okay, the last one is the trickiest of the bunch. The others are all, they're pretty hard to mess up, but this one is not. This one is a little tricky. This one says, AAS says, if 2 angles and a non-included side of one triangle are congruent to two angles and the corresponding non-included side of a second triangle, then the triangles are congruent. Now, do you see how this one could get messed up? Let me draw you a picture. What if we had something like this? Say we had this triangle, and we had this triangle. Okay, and I know this. I know we're going to label these. This is A, B, C, and this is D, E, F. Okay? I want to know, are these two triangles congruent? We'll do a little quick quiz here. So, what if... Are they congruent? By what? Angle, side angle. Okay, good. Perfect. That works. Okay, how about these two? So are they? No, because there is no AAA, right?
No. Oh.
Right? That's one of the ones that doesn't work.
Right.
Okay. Oop. Okay, how about this one? Okay, what would be the reason for that one? Angle, side, right? AAS. That makes sense? Angle, side, angle, side. Okay, how about this one? Ah. Now how come? It looks like I've got angle, side, and angle, side. Why doesn't that work? Ah, the wrong sides. They're not corresponding sides. It would have to be the side that's adjacent to the single loop angle would have to be congruent to the corresponding side on this one. It'd have to be these two, wouldn't it? It'd either have to be either this side and that side, or that side and that side, and neither one of those is happening. So that's an example where it would not apply, but that's kind of the tricky one. That's a little harder to see. And be careful about that one. Okay. So let's see if we can prove this. Oh, that one's easy. That one's just given to us, isn't it? That's just directly angle, side. Let's do a harder one. That way. Okay, try that. I've got two pieces there. Can I somehow come up with a third piece that's going to allow me to prove those two triangles congruent? Okay, think about it for just a second. Go ahead and check with your neighbor, see if you're on the same track. Okay, what do we got here? What do we think? Okay, how are we going to get, we've got two, how are we going to get a third angle? I hear it. Good. Perfect. Like that, right? Vertical angles?
No.
Okay, does that work?
Yeah.
Angle, side, angle, side. Yeah, it works because the non-included side is the one that's next to the single loop, or it's between the single loop angle and the blank angle, right? So they match up. Perfect. Okay, so if we want to, well, How about this one? Try that one. Okay, take a second, look at that. Get your notebooks out. It might be nice to be able to scratch this stuff down in your notebooks. Yeah, reflex is going to be one of them, yeah. Maybe talk it over, see if people agree. Okay, I'm hearing good stuff. I'm hearing good stuff here. I'm hearing from a lot of different places. I'm hearing that. Everybody agree with that? Okay, anybody with me, please? Okay. Okay, so that helps. The two triangles are sharing one side, and so we can use the reflexive property. That's good. 2 down, 1 to go. Can we come up with one more congruence relationship? What do you think? Caleb?
Couldn't you link, like, because maybe they're, like, parallel.
Okay. Okay. Now here's the suggestion. And by the way, this is a great hint. Okay. I'm going to want you guys from now on. I need to say this very clearly. I'm going to want all of you to be in chapter 4. Especially, even more than before, you better be using these notebooks. I'm going to start doing more frequent notebook checks because now is when I really want you to be. Shh. We've done a notebook check, haven't we?
No.
Oh, this is the class where we have. Okay, that's
Let's
okay.
just start now.
That's fine. Now is when, before it's been marginally important. Now it's really important. Because now when we start doing these congruence relationships, they get more complicated and we need pictures. And so when you're drawing these pictures, now what's going to happen in Moodle is you're going to get a picture like this. What I'm expecting you to do is kind of copy that down in your notebook, because a lot of times marking up those pictures makes the whole process a lot easier, like what we're doing when we can write the congruences in there, right? Now there's a suggestion here. The suggestion was, well, these look like parallel lines, right? And so if we extend these two lines, it's a great idea. Then this one looks maybe like a transversal, right? And if that were the case, I would have a transversal cutting through two parallel lines, and then like that angle right there, for example, and that angle right there would be alternate interiors, wouldn't they? It's a great concept, but what's wrong with my logic there? Did I make some assumptions there that weren't necessarily given to me? Yeah. Okay, good. It's a great idea, and we're going to see some stuff like that here real soon. And we're going to incorporate with problems like this. Had we been told the lines were parallel, that's exactly how we would have done it. But in geometry, we can't ever assume anything. Just because a picture looks a certain way, that means nothing. Always assume that the pictures are not drawn to scale, that they're drawn incorrectly. The only information that we can ever assume is stuff that's specific information about relationships, is stuff that's specifically given to us, either in writing, if they told us some congruences, or if they're marked in the drawing. So in this case, the only thing that we can assume about this is, well, we had some of it, right? We can assume those two sides are congruent, and we could easily show that that one's congruent to itself, but there's no other information there for us to use to get another congruent relationship, right? And so what's the answer? Is it possible to prove these triangles are congruent? No, not unless we're given some more information about them. Okay, so we can't. Okay, how about this guy? Now this one's a little messed up. Yeah, this is a little messed up here. I gotta go, let me do this. There. Okay? Now we're given some stuff. So here's a classic example of where we want to be writing this information on our picture. We want to make a picture and mark it up with the given information. So we're told that side UZ, or segment UZ, is parallel to WX. So that guy and that guy are parallel. How do we show that on the picture? Okay, the arrows. We'll use parallel arrows. Okay, everybody seeing that? Okay, we're also told that UW and ZX are parallel, so we'll make double parallel arrows there. And here's a great example of where now it might make sense for us to extend these things. Let's go ahead and extend these lines, these parallel lines. Maybe we'll need to do both, but maybe we'll just need one pair. And let's take this diagonal here and extend that as a transversal. And that might end up being helpful for us, right? Now, we're not given any congruences, but can we build 3 congruences here from our information that will allow us to show these triangles are congruent? Okay, what's one thing, what's a pretty obvious thing we can show right away that's congruent? Okay, good. This reflexive property. We know that WZ is congruent to itself, and it's a shared side. So there's a freebie. We got to get 2 more things. Caitlin's got an idea.
The parallel lines.
Now we got our parallel lines being cut by a transversal relationships from chapter 3. Okay, give me some numbers here that are going to be related, that are related by the parallel lines in the transversal, that share of one of our, corresponding, consecutive interior, etc. 1 and 3. How are 1 and 3 related? Alternate interior angles. Very good. And so we know by the alternate interior angles theorem, and I don't care about the theorem part, just alternate interior angles. Whoops, sorry, wrong. We know this, don't we?
We only have a minute.
Minute left? Oh, okay. Wouldn't 2 and 4 also be true?
Yes.
So we got it. What's the theorem? Real quick, what's the theorem? There it is. What is it? Angle side angle. There you go. Good. Okay, very nice.